So, Jai Hind. So today's topic is the Opamp, and this topic is has been taken from the subject Fundamentals of Electronics Engineering, which is currently running in the AKGEC syllabus of first year. And I am Neha Garg, assistant professor in EC department in Ajay Kumar Garg Engineering College. So today's topic is the Opamp, operational amplifier. So till now we have seen the transistor as an amplifier. Transistor is used in three modes, three configuration: common base, common emitter, and common collector. So common emitter is preferably used for the amplification purpose. So and Opamp is also used as a amplifier. But the difference between the BJT and Opamp is that BJT amplifies the single input signal. Like we have a V1 input, so it will be amplified by this common emitter amplifier. But Opamp has a two input terminals, like this input 1 and input 2. So this is the positive terminal here, and this is the negative terminal here. So if we apply V1 voltage here and V2 voltage here, so the input voltage is the difference of V1 minus V2. And this V1 minus V2 will be amplified by the Opamp here. This is the output. So output would be amplification of V1 minus V2. So Opamp amplifies the difference between the two signals, and this is the application of Opamp over the transistor. Means if we there is a noise signal, we are like singer is singing a song, so that song is having some noise also. So noise is added at both terminals, input 1 and input 2. So this noise, this is the signal V1, and with this signal V1 there is a noise also. Here there is a noise also, and with this signal V2 there is a same noise here. So if the same noise is introduced at both the terminals, so and this difference is amplified here, so this noise will be cancelled out with this noise, and this noise will not be amplified in case of Opamp. But in case of transistor there is no strategy, so that this noise can be removed. So basically this Opamp, this is the symbol for the Opamp, that this is the triangle, and inside this Opamp there are number of transistors are there. Like this is the common emitter configuration we have, like this is, and here RC is there, and plus VCC is there. So here we can give our V1 input, and here we can give our V2 input, and the output we are taking from this point. This is the V01 output, and this is the V02 output. So the difference between these two terminals is the output. So basically this Opamp, inside this Opamp, there are the common emitter configurations are there. So we are giving this input V1 and V2 actually at the input terminal of this common emitter amplifiers, and here we are getting the output. So we know in case of the transistors we require the biasing. This is the biasing that we have to give. Without this biasing, VCC plus and minus VCC, this transistor will not work. So that's why this Opamp will also require the biasing. We have to give the biasing here, VCC plus and minus VCC. So without, if we will not give any biasing to these pins, and we are giving the input, but output will be 0. So biasings we have to provide in case of the Opamp. And basically operational amplifier is a high gain differential amplifier. Differential amplifier is because we are amplifying the difference between the two signals. That's why it is a differential amplifier. And it's in case of the ideal Opamp, the gain is very high. In case of ideal Opamp, the gain is infinite. In case of ideal Opamp, gain is infinite. So if we give a very small amount of voltage here, the gain is very high. So output voltage will be very high. So maximum range of output voltage is limited by this VCC biasing. If we have given this VCC as 15 volt, so maximum output voltage will be restricted up to 15 volt. If we are taking this ideal Opamp and we are giving only here 1 millivolt, so in case of ideal Opamp, gain is infinite. So here the output will be the maximum possible output, and the maximum possible output is limited by the biasing that we provide. So maximum possible output will be in that case only 15 volt. So this is the symbol that we use. This is basically the Opamp. There is a 741 IC. This is the 741 IC. This is the pin number 1, pin number 2, pin number 3, and pin number 4, 5, 6, 7, 8, and this is IC 741. Here this pin number 1, it indicates the offset null, and pin number 2, it indicates the inverting input, pin number 3 indicates the non-inverting input, pin number 4 indicates the VC minus, and this indicates the VC plus, and this indicates the output, and this indicates the offset null, and here there is no connection. So here pin number 1 is pin number 2 is for the inverting input, and pin number 3 is for the non-inverting input. So these are the symbols for the Opamp here. So if we want to make only an inverting amplifier, inverting means like if I give here VI input at this negative terminal, and I ground this positive terminal, so this input is like in this way, so output will be in inverted form. So this is the inverting amplifier. Here output would be equal to V naught is equal to A VI and with negative sign, because this VI is applied at the negative terminal. So here output voltage will be equal to gain multiplied by input signal, that is Vi minus Vi, and this is in the open loop configuration. Open loop configuration. Open loop means there is no feedback here. Output is not connected with the input. So this is the open loop configuration and for your inverting amplifier. And if we want to make a non-inverting amplifier in open loop, we will apply Vi at this positive end, and this negative terminal will be grounded. And if we apply input signal here, so output will be in this form, and this output would be equal to A multiplied by Vi. Here the sign will be positive because the input signal is given at the positive end. So this is for the non-inverting. Non-inverting means we are applying input at the positive terminal. So this is the non-inverting, and this is for the inverting case. And these both configurations are in the open loop configuration, means there is no feedback from the output to the input side. And in open loop configuration, the gain of the ideal op-amp is infinite. So if we are giving the very small voltage here, our output voltage will be at maximum level, and that maximum level will be defined by these supplies that we are giving, V minus and V plus. And these are the symbols that we can use for the op-amp. We can use this symbol also, and we can use this symbol also showing the biasings V plus and V minus. And here the IC is 741. Here this pin is for the inverting input, this is for the non-inverting, and this VC minus and VC plus, this is used for the biasing. This biasing, that V plus and V minus that we have given here. And offset null is basically if we are giving, there is no input, V1 and V2, here input is 0. So our output must be 0 here. But due to some problem, or due to the aging of the instrument, or due to some mismatch of the transistor, we are getting the output voltage at the output terminal. So that output voltage is called the offset voltage. And to nullify that voltage, we have to apply equal and opposite polarity voltage at the input side, and that voltage is called the input offset voltage. So that pin number 1 and pin number 5, it indicates the offset voltage. So these are the ICs. This is the 741 IC that I told you in the last slide also, and this is for the dual Opamp 1458 device. This is also a IC, and here we can see there are two op-amps with inverting input. This is second pin is for the inverting terminal, third pin is for the non-inverting terminal. Here also we can see this pin number 6 is the inverting terminal and this is for the non-inverting terminal, and outputs are also there, and V plus and V minus are used for the biasing. Here we have removed the not connected, this part is removed and this part is removed and this part is removed, because generally they are not used in the experiments, so they are removed from this IC. And this is the how can we use the op-amp in a non-inverting non-inverting mode and inverting mode. In non-inverting mode, I have told you in the early slide that this Vi is connected with the positive terminal. So we are giving the input here and the output will be in same phase like this, and this negative terminal is grounded, and here positive terminal is grounded and input is given at the negative terminal. So output will be at this phase, opposite phase of the input. And here how we can connect the transistor with the input, like in single-ended input. Single-ended input operation results when the input is connected to one input while the other input is connected to ground. So in this case we can connect the op-amp in a inverting mode configuration or non-inverting mode configuration that we have discussed in the last slide. And double-ended differential input, in addition to using only one input, it is possible to apply signals at each input, this being a double-ended operation. So here we are applying input at both the ends, here also and at this end also. So that like here we apply V1 and here we applied V2. So the difference is V1 minus V2. So this is the VD. So this difference signal is given to the amplifier, and here output would be equal to gain multiplied by V1 minus V2. After that, common mode operation, like if we give a same input at both the terminals, like here also we have given V1, here we have also given V1, so output would be equal to V0 is equal to A times of V1 minus V2, and here V2 is also V1, so it would be V1 minus V1, so it would be 0. So ideally it should be 0, but practically a small output voltage will result at the output terminal. And in this case, if we find a common mode voltage, so common mode voltage would be equal to Vc would be equal to V1 plus V1 by 2. This is the common mode voltage that we can find in common mode operation. Common mode operation is generally preferred for the rejection of the noise, because if we have a signal here V1 and here signal V2, so V1 have noise like this and same noise will be added in both ends. So this noise will be cancelled out due to this difference in differential input. Now the how this op-amp works as a differential amplifier. So I have this basically op-amp has a different transistor inside, and different resistors and different capacitors also there in the op-amp. So this is the transistor, and we have given one input here and another input is at this point. And this is the common emitter configuration. We can see this is the emitter terminal and this is common in between base and input and output side. So the output will be taken from at this point. So here output is V01 and here output is V02. So the difference will be the V01 minus V02. So here it is assumed that both the transistors should be identical. The two identical transistors are both biased at the same operating point with their emitters connected together and return to the common rail by minus VE by the way of resistor RE. Now this is the differential input. When we give the differential input, so VD when separate inputs are applied to the op-amp, so in that case the input will be V1 minus V2, and common in case of the common input, the voltage will be Vi1 plus Vi2 divided by 1 by 2. Means if we are applying same voltage at both ends, so in that case the input voltage will be 1 upon 2 Vi1 plus Vi2. And output voltage will be given by both differential mode gain and common mode gain. So it will be the sum of the AD multiplied by VD plus AC multiplied by VC, where AC is the common mode gain and AD is the differential mode gain, and VD is the differential input signal and VC is the common mode signal. Now this is analysis with the opposite polarity input, means like this is our op-amp, plus minus, and we have applied V1 here and we have applied V2 here. So opposite polarity signal means we have applied V2 with different sign. This V2 is equal to minus of V1. So differential input would be equal to this is the minus, sorry, this is plus and this is minus. So V1 minus V2. So V1 minus V2, it would be equal to V1 minus if we put V2 is equal to minus V1, then it would be 2 times of V1. So that is written here also. In case of differential input, if we are taking the different polarity inputs, then in that case input voltage would be the 2 times. And in case of the common voltage, we will take the average of the two signals, so it would be 0. So in that case, output voltage would be equal to ADVD multiplied by plus in addition of ACVC. So by putting the values here, we will have a 2ADVS. So this shows that when the inputs are ideal opposite signals and there is no common element, the output is the differential gain times the input signal applied to one of the inputs. Now we are applying the same polarity input, like Vi1 and Vi2 both are equal to Vs. So in case of this differential input would be Vi1 minus Vi2. By putting the value of Vi1 here Vs and here also Vs, the output will be equal to 0. And here if we find the common voltage, input voltage, we will take the average. So average would be Vi1 plus Vi2 plus divided by 1 by 2. So here Vs plus Vs 1 by 2 is equal to Vs. Now we will find the output voltage, it would be equal to ADVD plus ACVC. So by putting the values here, we will have a ACVS. So this shows that when the inputs are ideal in phase signals, so no difference signal, the output is a common mode gain times the input signal. After that, op-amp specification. These are the different parameters that are used in the op-amp, like input offset voltage, input offset current, input offset voltage and input offset current, input bias current. So I have told you that output offset generally if we are not providing any input at the op-amp, like these are the minus, this is plus, and here input is 0 and here also input is 0. So our output must be 0. But this is not the case due to the mismatch of the transistor or due to the input offset current, or there is a output offset voltage is there. Output offset voltage is there. And to nullify this output offset voltage, we apply a equal and opposite polarity voltage at the input side, and that voltage is called the input offset voltage. And input offset current is also there. This is the we have the two transistors and the transistors should be identical. They should not be mismatched. If they will be mismatched, the current will be different. This IB1 and this IB2 must be same. If there is a difference in between both the current, there will be an input offset current, and due to this input offset current, there will be a output offset voltage. So output offset voltage is developed due to the input offset current and input offset voltage. So this is the input offset voltage. How we can calculate the input offset voltage that we require to nullify the output offset voltage. So here we can see this is the input offset voltage that we applied at the input side to nullify the output offset voltage. So we can due to the virtual ground, the potential at this point and this point would be equal. So this point is grounded, and this point the potential would be equal to Vi naught. Virtual ground means, like in case of the op-amp, like this is the op-amp, minus and plus, we have we have grounded the positive terminal, and here there is a resistance is there. So in case of the op-amp, gain is infinite. Gain is infinite means, like A is infinite, means V out upon Vd. So Vd is Vi, input voltage that we are giving. It should be 0. So it means we are applying V1 here, we are applying V2 here. So V1 minus V2 should be 0. Or we can say that V1 and V2 must be at the same potential. So if we have done the V2 at ground terminal, so this potential will also be 0. So this is called the virtual ground. So similarly, we have connected this plus with V1 naught and same potential are there at the V1 naught here. So here and there is a here the current IB1 and IB2. There is no current flowing in the op-amp also. In ideal case, there is no current flowing in the op-amp also, because here the potential difference is 0. So that's why there is no current is flowing here. All the current that is coming from here, it flows through this path. So and this potential is Vi naught. So at this point the potential will also be Vi naught. So we can find the output voltage V naught is equal to A times of Vi. So Vi would be equal to, at positive terminal we have applied the Vi naught. So I have written here Vi naught. At negative terminal the potential is V naught is feedback from here. So we can take this R1 upon R1 plus Rf multiplied by V naught. We can consider this part in this way. This is the Rf, this is the R1, and this whole is the V naught, and we have to find the potential at this point. So this would be equal to R1 plus Rf multiplied by V naught. So this potential is written here. This potential indicates the potential at this point. So by solving this, we can obtain this value. So this is the output offset voltage due to the input offset voltage. V offset is there. After that, input offset current. So an output offset voltage will also be result due to the difference in the bias current at both the ends. So output offset voltage is basically produced due to the input offset voltage or due to the input offset current. And input offset current is flowing due to the mismatch of the transistors. If the transistors are not identical, then their base current will not be same. So since the two input transistors are never exactly matched, each will operate at slightly different current. So this is the current that is flowing here. Ideally this current should be same, but practically due to the mismatch of the transistors, this current is not same. That's why due to this current, there is a output offset voltage at the output terminal. So this is the output offset voltage due to the input offset current. So here we can see at the positive terminal, we can current IB is flowing here, and it is at the negative terminal. So we have put here negative symbol, and here this is the positive. This positive current is flowing here, and the potential drop across the RC would be equal to IIB RC, and it would be equal to IIB R1. So here at the negative terminal, the output voltage would be equal to V naught is equal to minus Rf upon R1 and equal to Vi. And for non-inverting case, it would be equal to 1 plus Rf upon R1 multiplied by Vi. So we are putting the simply we are putting the values here. V naught at the for the negative terminal, inverting input case. So here the potential is this much at the inverting end, and minus Rf upon R1. So Rf is this much, R1 is this much. And for non-inverting terminal, we have 1 plus Rf upon R1. This much the potential here, and 1 plus Rf upon R1. So at due to this both these currents, the output voltage will be the difference of these two. So by solving this, we will be having output offset voltage will be this much, IIO multiplied by RF, and this IIO is equal to IIB plus minus IIB this. So this is the output offset voltage. So we have calculated the output offset voltage due to the input offset voltage and input offset current. So this is for the output offset voltage due to the input offset current that we have calculated in the last slide, and this was this much. This is this IIO, this is the input offset current, and this is the total output offset voltage that is given by the output offset voltage due to the input offset voltage, output offset voltage due to the input offset current. So summation of this will provide the total output offset voltage. After that, we can use the Opamp in open loop configuration and in closed loop configuration. But in idle Opamp, it has some characteristics, like it has gain is infinite. Idle Opamp characteristics: gain is infinite, input impedance is infinite, output impedance is 0. CMRR is infinite, slew rate is infinite, and bandwidth is infinite. So these are the characteristics for the idle Opamp. And open loop configuration, gain is very high. So generally, if we plot a graph between the input voltage that is the difference between V1 minus V1 and V2, and output voltage, so it would be like in this pattern. It will be in this way, like in this way. Here it will be plus V set, and here it will be minus V set. This is the V input, and this is the V output. Means if we are changing the input in open loop configuration, the maximum output that it will be obtained will be a V set, plus V set, and minus V set. So generally this is the linear region of the Opamp. So this in linear region we can control the output of the Opamp, and in this region, saturation region, we cannot control the output of the Opamp. If we apply a 1 volt or 2 millivolt or 3 millivolt, since its gain is infinite, so it will automatically switch to a very high output voltage, and this output voltage will be limited by the supply biasing that we have given in the Opamp. So generally we preferred Opamp in the closed loop configuration, in which we will give a feedback from the output to the input, and that feedback will always be given in the negative side, like this is the negative and this is the positive. So always there will be a feedback from negative terminal. This is the RF and this is the R1, because in negative feedback will reduce the gain, and gain in open loop gain is infinite. So by giving the negative feedback, stability is increasing and gain is decreasing. So while making inverting mode configuration or non-inverting mode configuration, in both type of configurations, the feedback will always be negative side. If we want to make it as a inverting amplifier, so we will feedback will be same, and here we will make it ground, and here we will make ground connected Vi. And if we want to make it as a non-inverting amplifier, so here feedback will be same, like in this way, and here we will apply Vi, and this part is grounded. So this is for the non-inverting and this is for the inverting. Feedback will always be given in the negative side so as to gain is reduced. So this is the inverting Opamp, and this is in the closed loop configuration. So output voltage is there, feedback is there, and R1 is there. So in this case, if we want to calculate the output voltage, and we know that in case of idle Opamp, gain is 0. So in previous slides I have told you the concept of virtual ground. So due to the virtual ground, this positive terminal is grounded, so here potential is 0. So here at this point the potential would be equal to 0, and all the current that is coming from here to here, there is no current flowing at this end. So all the current will pass through this resistor RF. So we can by applying KCL, we have a V1 upon R1 is equal to minus V0 upon RF, because V1 minus 0 upon R1 is equal to 0 minus V0 upon RF. So V0 would be equal to minus RF upon R1 multiplied by V1. So this is the equation of equation of output voltage with respect to input in case of inverting domain. And also we can represent it as V0 is equal to A Vi. So here A would be equal to minus RF upon R1. Okay, so this is the same derivation that I have done in the previous slide. So this is your feedback resistance. If we take the feedback resistance as 10 kilo ohm and this is 1 kilo ohm, so and gain is your V0 is equal to minus RF upon R1. So here the gain will be 10 times of Vi. Now this is the practical Opamp circuits that we will see: inverting amplifier, non-inverting amplifier, unity follower, summing amplifier, integrator and differentiator. So inverting operational amplifier, so this we have seen that positive terminal we have grounded, and at this terminal we have applied the VIN signal, and this difference is amplified here. So this potential is 0. So at this point the potential would be 0. So current would be equal to this VIN minus VIN upon RIN is equal to minus V0 upon RF. So same derivation is given here. We have obtained the value of minus RF upon R1 in the previous slide. After that, non-inverting amplifier is there. So in non-inverting amplifier, we have feedback will always be there in the negative side. So there is a feedback, RF is there in the negative side only, and positive side we have given the input signal, and in negative side feedback is there and also it is grounded. So this is a non-inverting configuration in closed loop. Closed loop is there because there is a feedback in the Opamp. Now due to the virtual ground, this VIN at this point its value would be VIN. So by applying the KCL and KVL here, we can find the output voltage here. Like if we see, this is a plus and this is minus and this is plus. So here we applied the VIN, and here this is the circuit. So this is the RF and this is the R1, and here it is grounded. This is the V0. So this is basically your non-inverting amplifier. The simple form of this circuit is in this way. So here this is VIN. So here the potential would be equal to VIN. So if current is coming from this point to this point and no current is flowing this, so whole current is flowing through this point. So by applying the KCL, we will be having 0 minus VIN upon R1 is equal to VIN minus V0 upon RF. So V0 upon RF is equal to VIN 1 upon RF plus 1 upon R1. So it would be equal to V0 is equal to VIN RF R1 plus RF. Now here RF would be cancelled out. So output voltage would be equal to VIN 1 plus RF upon R1. V0 is equal to VIN 1 plus RF upon R1. So this is the output voltage in case of the non-inverting amplifier in in closed loop configuration. Or we can see here the value of gain is here 1 plus Rf upon R1. This is the value of gain here. So here also, so the same derivation is there that I have discussed in the last slide. We can see in lastly we are getting the output. Gain is there 1 plus Rf upon R2. Here we have replaced R1 with the R2. After that, voltage follower. So voltage follower means that what we are giving as an input, the same we are obtaining as an output. Voltage follower provides the it acts as a unity gain buffer. And how it is made? It is made by making the feedback resistance Rf equal to 0 and resistor R2 equal to infinite. Like in case of the negative non-inverting amplifier, we have this is minus and this is plus. So we apply VIN here, and this is grounded. This is R1 and this is RF, and this is output voltage. So this is the non-inverting amplifier. And if we are putting here R1 as infinite and RF as 0, so this circuit will be reduced into this circuit. We will see this in this way. Okay, like there is a feedback, unity feedback from the output side to the inverting terminal, and positive terminal is connected with the VIN input. So in case of the non-inverting amplifier, we have seen the output is related with the input 1 plus Rf upon R1 multiplied by Vi. So we have put the value of Rf as 0 and R1 is infinite. So this equation will be reduced in the form of V0 would be equal to Vi. So same thing is there. V0 is equal to Vi. It means gain that is equal to V0 upon Vi. This gain would be 1. So in case of voltage follower, the gain will be 1. If gain is 1, so what is the use of this voltage follower? Because this voltage follower, it acts as a buffer. It provides a high input impedance, but it does not provide any gain. The input that we are providing, the same is obtaining from the output also. So this is basically used for providing the delay in the circuit or providing the high input impedance. After that, summing amplifier is there. So summing amplifier, here we can see at negative terminal we have connected different resistance here, and input voltage is V1, V2 and V3 is there, and output non-inverting terminal is grounded. Basically summing amplifier is used to add up the different input voltages. Like here different voltages are V1, V2, V3. So this is used for, this is another type of Opamp amplifier configuration that is used to combine the voltage present on 2 or more inputs into a single output voltage. So here we can see the positive terminal is grounded and negative terminal is given the supply V1, V2 and V3. So if we see the combined output, so combined output would be equal to V0. We will take, first of all we take V1. So from V1 it would be equal to Rf upon Rin, Rf upon R1 from, this is for V1, and after that Rf upon Rin for V2, and after that Rf upon Rin for V3. So basically it would be equal to Rf upon Rin minus and this is V1 plus V2 plus V3. So all the input voltages will be added here, and finally it will be divided by Rf upon R1 multiplied by Rf upon R1, and output voltage would be, so here we can see V1 upon Rin, V2 upon Rin. So ultimately the output voltage would be equal to, we can see Rf upon Rin, V1 plus V2 plus V3, etc. Number of voltages we are connected and at the inverting in terminal, and we can obtain the output in this way. After that, difference amplifier is there. So difference amplifier, here we can see R1 and R2 is there. V1, V2, we are connecting the providing the V1 at the inverting input and V2 at the non-inverting input, and output is there here. So this output will be the here the input signal will be the difference of both V1 and V2, and we have applied the input at inverting input also and non-inverting input also. So output due to the inverting input is minus R3 upon R1 multiplied by V1, and output due to the non-inverting input so we have to take the voltage at this point. So voltage at this point would be equal to the potential across this point, and along this point we have a voltage V2. So across this R4 we have a voltage R4 upon R4 plus R2 multiplied by V2. So this is the potential, this is our VB, this is the potential at this point VB. So for output due to the non-inverting amplifier would be equal to V0 would be equal to 1 plus R3 upon R1 multiplied by VB, and 1 plus R3 upon R1, the value of VB will be taken from this equation, and it would be equal to R4 plus R2 multiplied by V2. So this is the output voltage due to the inverting terminal. This is the output due to the non-inverting, and this is the output due to the inverting. So total output will be the addition of this inverting and non-inverting part. So these are the characteristics for the ideal and practical op-amp. So ideal op-amp has a characteristics like it has a infinite voltage gain, zero offset voltage, it has a infinite bandwidth, and it has a zero output impedance. It has an infinite input impedance, but practically these are not possible due to the imperfections in the manufacturing of practical op-amp. And practical op-amp holds the following characteristics. The open loop gain of the practical op-amp is around 7000. Practical op-amp has non-zero offset voltage. The bandwidth of the practical op-amp is very small value. The output impedance is in the order of hundreds. The input impedance is in the order of mega ohms only. So these are the characteristics of the ideal op-amp and the practical op-amp. In ideal op-amp we have seen the gain is infinite. So if we are giving the very small input voltage, we are getting the maximum output that is limited by the VCC plus VCC and minus VCC. And also there is a zero offset voltage. So if we provide a zero offset voltage means if we are giving a input at the op-amp and that input and output, if we are giving the zero input at the op-amp, the output must be 0, but the output is not 0, but there is some value of the output because due to the mismatch of the transistor, or it may be due to the offset current, and it must have an infinite bandwidth also. So this we will discuss in our next lecture also, and it has zero output impedance and infinite input impedance. So like FET FET also has a high input impedance and low output impedance. So practically Opamp has does not has some these characteristics. So practical Opamp has non-zero offset voltage, and bandwidth of practical Opamp is very small value. The output impedance is in the order of hundreds. The input impedance is in the order of mega ohms only. So this is all about Opamp. Thank you.